This is a second lecture over the calculations for tangent, binormal, normal, curvature, and torsion for space curves. In this lecture, the parameterization will be an arbitrary parameterization. In the first one, it was the arc length parameterization. We'll see that the results are very similar. In fact, it's very easy to derive these results from the arc length parameterization. A reason for using the arbitrary parameterization is that usually it's impossible or impractical to find the arc length function. It usually doesn't have a closed form solution, so it's impossible to reparameterize your curve into the arc length function and use those equations that we derived before directly. The derivation of the tangent, normal, and binormal follow the same pattern here. You take successive derivatives and make unit vectors and name the magnitudes and name the unit vectors. But there's one other result that makes this work for your arbitrary parameterization, and this is the derivative of the arc length function. Okay, here is the arc length function. S of t is integral from some starting point, I'll say a to t, of the magnitude of the first derivative of the parameterization, the first derivative r prime of tau d tau. So by the fundamental theorem of calculus, the first derivative ds by dt, this is the derivative of the arc length function, is equal to the magnitude of the first derivative, or if you're thinking in terms of a space curve traced out by as a path of an object, this is the magnitude of the velocity of the object as it goes along the curve, or in other words, its speed. So we begin just like we did before. We have some parameterization for the space curve, and we take its first derivative. In this case, the first derivative is not necessarily anyway, a unit vector. So we separate it out as a magnitude and a unit vector, just like we did before. The unit vector is the tangent vector. This magnitude gets used later, but right now we're not using it. So you just take the derivative, find the unit vector associated with it. That is your tangent vector to the curve. Now proceeding as before, we take the first derivative of the tangent vector, but instead of just taking the derivative, let's use the chain rule. We could write this as the derivative of the tangent with respect to the arc length times the derivative of the arc length with respect to t. And now you can see why we pointed out the results earlier, that ds by dt, let me write it here, in that first slide that we were looking at, ds by dt equaled the that's the magnitude of the first derivative. So we can write that, and now we have ds by dt. But we know what ds by dt is from our arc, that's the arc length derivative. We know that's kappa n. Right? So we can substitute that, and we have that the first derivative of the tangent with respect to time equals the magnitude of the velocity times the curvature in the direction of the unit normal. And this is the same unit normal that was derived for the arc length parameterization. And we can use this expression to find the curvature when we actually do some work with real curves. The binormal is defined just as before. It's a cross product of the tangent, the unit tangent, and the unit normal. Now we're going to find the torsion by taking the first derivative of the binormal. If this sounds very familiar, it is. You're doing exactly the same steps. And now we're going to do again what we did for the tangent vector. We'll take the derivative with respect to s times ds by dt. So we've used the chain rule here, remembering that ds by dt is as the magnitude of the velocity, and then we of course have that arc length derivative of the binormal. Here was the expression from the first lecture. The arc length derivative of the binormal equals minus the torsion in the direction of the unit normal. We can substitute that in, and we have an expression here for the first derivative of the binormal with respect to time. And we can use that to find the torsion itself. Okay, I'm not going through the steps, but we have a similar result for the first derivative of the unit normal. Again, we see these scaling factors of the magnitude of the velocity along the space curve for the parameterization, multiplying the curvature and the torsion. I'm going to write here, if we had dn by ds, this is for arc length parameterization, is torsion, scalar torsion multiplying scaling the binormal unit vector minus kappa times the tangent vector. This is for arc length parameterization. Here we have it for arbitrary parameterization. The only difference are the scaling factors of the magnitude of the velocity, which is the magnitude of the first derivative of your parameterization. And we get the general results which we expected. The unit T, B, and N vectors are the same for all parameterizations. The curvature and torsion are the same. If you remember from the first lecture, I said these are the invariants. These are these vectors and these scalars are associated with the image of the space curve and not with the parameterization. And here are the Frenet equations, and you'll see it's exactly as before. We have the same skew symmetric matrix, multiplying the same vectors. The only difference is a scaling factor that has to do with the particular parameterization. And now in the next lecture, I'll show how to apply this to some problems in mechanics.